So we are in the middle of respiratory, so we're looking at alveolar ventilation. And remember I said before that when you're looking at the alveolus, so you're looking at the air that you breathe in, the most important part of it is what's in contact with that respiratory membrane, because that's the only part that's going to get exchanged with the capillaries, because that's where the capillaries are. So there's not any capillaries associated with any other place in your body. We have a term for that. That is to say the non-physiologically productive air that's in you. We call that dead space. Okay, so there's a couple of different types of dead space. There's anatomical dead space. This is basically air that's essentially in the passageways. So if it's in your trachea, air that's in the bronchi, in the bronchioles even, this is basically air that's not in contact with the respiratory membrane. So that's called anatomical dead space. And so the important thing, the anatomically or the physiologically active or important area where the exchange surfaces are is only in the alveolus. And it's not only just in the alveolus, but it's actually only in living functional alveoli. Which basically brings me to my next type of dead space, which isn't actually on here, but it is mentioned in some textbooks. There's another potential type of dead space, which is called physiological dead space. These are essentially associated with non-functional or damaged alveoli. So if you've incurred some lung injury or something of that nature, or smoking, or something of that nature, and you damage some of the alveoli, then those alveoli are physiologically offline. So that's physiological dead space. So ultimately then, when you take a look at your alveolar ventilation, it's going to be the lump total of the air that you breathe in, that's your tidal volume, minus all of your non-functional air, which is your anatomical dead space and your physiological dead space. So that leaves you now to only the functional volume. That's the volume of air that's in contact with the respiratory membrane. And then you multiply that by your respiratory rate. So when you're looking at that ventilation, it's the amount of functional air, that's air in contact with the respiratory membrane, that you're breathing in as a function of your respiratory rate. Now, let's take a look at the gas, and we're going to move quickly through this because this comes to some of our gas laws, right? So Dalton's law, right? So when we take a look at the gas that's actually in the alveolus, in the alveoli, basically, you have a gas that's a little bit different than atmospheric, right? So you're going to have a little bit less oxygen than atmospheric, right? That's because you're absorbing it. And you're going to have more CO2 because you're taking it on, right? That makes a lot of sense. So you're loading CO2 in there, you're taking out the oxygen. But ultimately what happens is the air that's in your alveolus as it's going out will run into the air that's already in your bronchioles. That's the dead space air. And when that happens, then those two air masses mix together. And then what you get is sort of a midpoint, right? The air that's in your dead space is atmospheric. And so what you get then is a mixture of the air that's exhaled. So it's a little bit of both. And so that's I mean, you kind of get into that nitty gritty if you really, really get the deep woods of pulmonology and respiratory physics. But when we take a look at volumes, we want to basically take a look at, there's a lot of other volumes that we look at. There's volumes and what we call volumes and what's called capacity. And so ultimately then, when you look at your pulmonary ventilation, you have your tidal volume, your alveolar volume, and your expired volume. Basically, all of this is going to be determined by obviously your respiratory rate and the amount of your tidal volume. Or your tidal volume you can change. You can breathe in more, you can breathe out less, that sort of thing. And so you can increase your tidal volume. And if you increase your tidal volume, obviously you're going to be increasing your alveolar ventilation rate. You're going to be bringing in more oxygen, more air into the alveolar sacs themselves. right? So if that's basically the easiest way, obviously, to increase the actual amount of air in your alveolus. So that's the reason why we control and we regulate our respiratory rate, is so that we can increase the amount of air in our alveoli. Now, if you think about that, what you're talking about, if you go back to our economics analogy, when you're increasing alveolar ventilation, what you're doing is you're increasing your oxygen. And remember, from our economic thing, oxygen is your product. So this is your supply side. Where we had supply, we had demand, and we had distribution in between. Cardiovascular system was the distribution system that basically feeds demand. The supply is here. This is the supply. So your bodies are screaming for oxygen. And so if they scream loudly, if your demand goes way up, then your supply has to go up as well. So that's the reason why you're controlling respiratory rate and your tidal volume amount. So you can basically get enough oxygen to meet that supply. So let's take a look at a couple of different pulmonary metrics here. So we have a series of what's called volumes and capacities. And capacities are essentially the summation of multiple volumes. That's typically what it is. And so we have a couple. We've already met tidal volume, right? That's your sort of resting in and out. There's also three others. There's one that's called the expiratory reserve volume. So this is basically the top of your breath. So if I told you to breathe in, inhale as deeply as you can, go all the way up to the top of your breath. That's expiratory, that's inspiratory reserve. Expiratory reserve is the bottom of your breath. Sorry, I'm usually doing these in the opposite direction. I always stop top down. So this is the bottom of your breath. So in this case, what I want you to do is I want you to breathe out all the way down as far as you can go. That's expiratory reserve. You're expiring, or you're breathing out as far as you can go. Then inspiratory reserve is the top of your breath. This is the one where if I tell you to breathe in all the way as far as you can go at the very, very top. When you can't go any further, that's your inspiratory reserve. That's as far as you can go. That represents your ceiling of capacity. Your expiratory reserve represents your floor of capacity. And then the residual volume is sort of like the leftover volume after ERV. So even if I tell you to exhale all the way down to the bottom of your breath until you can't go any further, you still have air in there. That's residual volume. So ultimately, you have your normal respiratory cycle. You have the amount of breath that you can go down to the bottom of your breath from expiratory reserve. And inspiratory reserve is your ceiling. So this is your floor. This is your ceiling. And then the residual volume is basically what's left after your maximum exhalation, of which a component is what we refer to as minimal volume. Minimal volume is the air that's associated with the collapsed lung. So residual volume is a combination of volume that's beyond ERV, but you can get to it. So you can train your diaphragm to get a little, to drop your floor a little bit. Not a lot, but you can drop your floor a little bit. Okay, so you can tap into that residual. But even if you took your lungs out, squeeze them, just wrung them all out, just wrung them completely dry, like a washcloth, right? Like just wringing that washcloth as tight as you can. Can you get all the water out of that washcloth? No, because even once you get to like the maximum amount of wringing, I mean, you can't get anything else out of it. It's still kind of damp, isn't it? So that's like minimal volume. You can never get that out, right? That's the leftover. That's what minimal volume is. So those are the major volumes that we have. Now let's take a look at the capacities, because remember, capacities are associated with a summation of volumes. And so inspiratory capacity is your ability to take a full inspired or inhalation breath. It starts at the trough of tidal volume. And then basically what happens is you start with your tidal trough, and then you just basically keep going up. You go through tidal volume, and then you go all the way to the very top of your breath, the inspiratory volume. And so the summation of tidal volume and inspiratory reserve is your inspiratory capacity. That's your ability to take in a deep breath. Okay. Now, Your functional residual capacity, the FRC, is basically your expiratory reserve volume. So that's basically going from your tidal volume down to the floor of your expiratory reserve. So it's that one plus your residual. So that's all of your floor. So the stuff you can get to and that stuff that you can't get to, right? That's the residual volume. And so the two of those sum together what we call functional residual capacity. So it's everything you have below tidal. That's essentially what it is. The most important one, I would argue, is probably vital capacity. This is the one that you can get to normally. So if I were to tell you, take in the deepest breath you can, go all the way to the top, and then slowly exhale it all the way out to the bottom, that is what you have access to muscularly. So the muscles that you have, the way they're conditioned, the way they're toned, that's what you have access to. That's called vital capacity. So it's your expiratory reserve all the way down to the bottom, plus your tidal, plus your inspiratory reserve all the way to the top. Okay. So your complete full breath from the very bottom of the floor to the very top of the ceiling is your vital capacity. Now, generally speaking, when you are conditioning for sports and you're trying to increase your breath, like swimmers do this a lot, right? When you're training yourself to hold your breath and to sort of do deep breathing so that you can actually do whatever it is that you do. Singers do this a lot sometimes. Woodwind folks do this a lot when they have to play a lot on a single breath, that they have to kind of like learn how to increase their capacity. And so you can train yourself and condition yourself to increase the ceiling a bit and drop the floor down so you can get a bigger volume of vital capacity so that you can work with that longer. That's what's happening when you take a deep breath and you're ready to kind of sing out a note that lasts forever. That's what happens. You go all the way down to your bottom floor, that is to say your ERV. So that's an important one that we oftentimes will measure. If you go to pulmonology, do like a pulmonology visit, that's what they want to measure, because on any given day, that's what you have access to. So the other one that's also important is total lung capacity. This is basically your vital capacity. That's pretty much everything you got access to, plus the stuff you don't have access to, which is the residual volume. So that's the whole kit and caboodle. This is everything, including minimal. So every scrap of air in your lungs, that's total lung capacity. And so the way that you measure these capacities is with a pulmonary function test, where you're basically measuring the rates and volumes of the movement of the air. Now, oftentimes what you do in a pulmonary function test is you want to measure what's going in, right? So you want to measure the inhale. The problem is when you're inhaling, it's like negative space. It's like negative pressure. So you can't actually have an instrument on your mouth and measure negative pressure, which is the reason why they always have you blow out, right? Because the idea is if you can't blow out, then you can't get it in either, right? That's kind of the idea. And so this is kind of what it looks like. So here you can see you've got your volume of air versus time. So here you can see the gentle oscillation of your tidal volume. And then as you breathe out, go all the way down to the bottom of your breath, you've got your ERV. So that's from the trough of your tidal down to the very floor, the bottom of your breath. You go back into tidal. From your trough, you go through your tidal and keep on inhaling all the way up to the very top till you can't go any further. That right there is your, that's actually your inspiratory capacity. So going from the tidal trough to the peak of your inspiratory reserve is your inspiratory capacity. But from the tidal peak to the inspiratory reserve peak is your inspiratory reserve. Okay. So it's your tidal, and then you go further, you go beyond. There's more there that you can tap into. Then your vital capacity is represented by the very top of your peak to all the very bottom of your floor. So it's from the peak of inspiratory reserve down to the bottom of expiratory reserve, so ERV, and your tidal volume as well. And then your functional residual is from the trough of your tidal down to pretty much zero. So that's everything that's below tidal. And this is what your curve should look like. So if you did a pulmonary function test and you're just basically breathing normally, it should look something like this. Now, This is just volumes. But remember, we said in a pulmonary function test, you're always looking also for rates. And those rates are important as well. There's a reason why. Because even if you're a smoker and you're respiratorily compromised, you're still going to get your volumes. Like if you look at a pulmonary function test, a smoker who smokes heavily and has problems is still going to get their air. They're still going to get the same volume. The issue isn't whether or not you get your same volume. The issue is how hard you have to work to get it. And you see that in the rates. So oftentimes when you see a pulmonary function test, what you'll see, the rates are the slopes of the lines. So generally speaking, like on a good inspiratory reserve with the exhaling on the other side. So this is your inhale. This is your exhale. What you should see is like about a 45-degree angle going in and then coming out. And that's good. What you see in somebody who's respiratory compromised is oftentimes what'll happen is you'll see a steepening of that slope. That means it's a faster rate. It's coming in fast and then it'll kind of shoulder off. That means you're sucking it. It's like you're gasping. That's what that means. So if you have a sharp peak like that with a little bit of a tail more like that, that means you're gasping. So as you're inhaling, it's like, so that's what's happening. But on a pulmonary function test, you can't hear that from somebody who's just standing next to you. But on a pulmonary function test, you can actually see that on the changes of these slopes. So when we do that pulmonary function test, sometimes we do that, sometimes we don't. It depends on whether or not the gods favor us, which they're not really this semester. I'm just waiting for the lightning bolt any moment now. But you can actually see that on the pulmonary function test. So it's always good. I always look for smokers, like really, really heavy smokers. They're getting harder to find these days, or they admit to it. Because a lot of times, and I ask them, it's like, well, how much do you smoke? And how long have you been smoking, right? Because has your respiratory system been compromised? Has it had to adapt? And sometimes we'll see that when I see a heavy smoker who smoked for a very long time. You'll see that sharp incline in the inhale with a shouldering of the exhale. Or sometimes you'll see both. It was like, so that'd be sharp up, sharp down, sharp inhale, sharp exhale. So it's like they're pulling it in very strongly and they're pushing it out very strongly. So it's more of a forced breathe. And so ultimately then, this is obviously all to get your volumes in so that you can essentially get that alveolar air in contact with your respiratory membrane so that you can get gas exchange. Now, gas exchange depends on a couple of things once you're there. Okay, so once you have your air in your alveolus, you also have to deal with your partial pressures, right? Because it's all partial pressure of oxygen that you're interested in, not the entire mixed gas. For instance, most of the air that's in your lungs right now is nitrogen. But we don't care about nitrogen. We only care about oxygen. Matter of fact, we don't really care about oxygen per se. We only care about the partial pressure of oxygen that's in our alveolus in contact with the respiratory membrane. Wow, say that fast. Right? It also depends on diffusion. This is where Fick's law comes in, right? This is the reason why the respiratory membrane is so thin. So this gets us, obviously, we've already talked about Boyle's law, right? This basically is governs how we change our volumes in order to manipulate pressure so that we can actually get air into our lungs. However, we also have Dalton's law, right, which is the law of partial pressure. That is to say that the pressure of a mixed gas is the sum of all the partial pressures of the component gases. And what are the component gases of air? Well, we've got nitrogen for one. That's actually the major component of our air, which is more than 3/4 of our air by percentage. Oxygen's coming in around 21% normally atmospherically. Water vapor is out there about 0.5%, give or take, depending on whether you live in a humid environment or not, or if it's raining or not. Carbon dioxide is generally supposed to be fairly low at 0.04%. Of course, if you're in cities, that's probably going to be a little bit higher. And if you're in the country, that's going to be probably a little bit lower. But this is your mixture. So these are your partial pressure, or these are your percentages rather, that leads to your partial pressures. And so the combination of all these mixed together gives you your total atmospheric pressure, which we already said before, is 760 millimeters of mercury or 1 atmosphere. And so that's your total pressure, atmospheric pressure that we're dealing with, that we talked about when we're talking about this sort of little dance that we do between intrapulmonary pressure versus atmospheric pressure when we're talking about inhaling, the inhaling mechanism, right? Manipulating our pressures. So ultimately then, even though our atmospheric pressure is 760, all we really care about is the partial pressure of the gases we're interested in. So the partial pressures of the gases we're interested in exchanging are oxygen, primarily. We want to get that one in, right? And carbon dioxide. What does that mean? That means we want the partial pressure of oxygen outside, atmospheric, to be high, yes? And the partial pressure of oxygen inside, the alveolus, to be low. Why? Because if we set up that pressure gradient, then the oxygen is naturally going to want to flow down its pressure gradient from the outside, that is from the atmospheric gas, into the alveolus, right? And so if we go from the alveolus to the capillary, we want it to be even lower still, so that it continues to move down its pressure gradient into the capillary. That's diffusion, following its pressure gradient. We want CO2 to be doing the opposite. We want CO2 to be really high in the capillaries, which it is because you picked up the trash, and so you're heavy laden with trash. You want it to be a little bit lower in the alveolus so that it basically goes from high to low, and you want it to be lowest of all in the atmosphere so that it can continue to move through to the outside, right? And so that's basically what you want to set up. This is the reason why it's not just the pressure, it's the partial pressure that you want to look at. And that kind of gets us also to the next law that we talked about already. That's Henry's law, right? This is the solubility law. And this is basically where this is temperature and pressure affects the solubility of a gas. And so the amount of gas in solution is a combination of their partial pressure and their temperature. Right, so increasing temperature decreases solubility, and increasing pressure increases solubility, where we talked about that a little bit. And so this is important because ultimately the gases that you are inhaling are in, of course, the gas form, yes? But oxygen in your blood has been dissolved into your blood, which is what? Liquid. So in order to get oxygen and CO2 to diffuse, you have to cross this gas to liquid barrier, which means solubility is important to you. So you have to make sure that not only do you have the pressure gradient of oxygen to go in, but you also have to have the solubility in your favor so that it will actually dissolve in the liquid, hello Henry's law, so that you can get that into the blood, because the blood is a liquid-based system. That's why we talk about Henry's law, is because it has to solubilize into our blood or saturate our blood. So let's take a look at the solubility of these gases in our body fluids. So CO2 is very soluble, which is helpful because we can move it around quite easily. Oxygen, not so much. And nitrogen, hardly at all. So that's the reason why we can basically suck in as much nitrogen as we want, and it does nothing. So it doesn't ever cross our membrane, even though the concentration is really high. The pressure gradient favors it strongly, right? Because there's a lot of nitrogen in the air. There's not so much in our body. So you would think that by pressure gradient, by diffusion, nitrogen should be screaming to get into our bodies. But it doesn't. Why? Because it's not soluble at all. So if you don't have solubility, then it becomes a barrier. So you have to basically make sure that your gases are soluble and that you have a pressure gradient. So notice all these little things that have to go just right in order to get your gas exchange. So let's take a look at the partial pressures. This is in pulmonary vein plasma. So the partial pressure of CO2 is roughly coming in right around 40 millimeters of mercury. Oxygen is about 100 millimeters of mercury, and then nitrogen is about 573. So you can see very, very high partial pressure. According to the partial pressure difference, then nitrogen should want to be in the blood. It should want to diffuse strongly into the blood, but that solubility is a barrier. It keeps it from doing that. So that's the reason why nitrogen just comes in, and nitrogen just goes right back out. Carbon dioxide freely solubilizes, so it moves quickly, so does oxygen. And so ultimately then, what you do is you basically have to set up your diffusion rates once you got your solubility situation solved so that you can cross your respiratory membrane. So ultimately, this sets up the diffusion mechanism for your gas exchange in your alveoli. Okay, so combination of the partial pressures, Dalton's law. You got the air in there in the first place by Boyle's law, right? And then Henry's law removes the solubility barrier so that these gases can exchange along their pressure gradients. So what does this give us? This gives us, first of all, really strong differences in partial pressure that facilitates gas exchange. The distances are short, that also facilitates gas exchange. They're lipid soluble, that's solubility, right? That's in the numerator of Fick's law, that facilitates gas exchange. The surface area is large because they're capillaries, right? That facilitates gas exchange. And the blood pressure and the airflow are coordinated. That's a pretty big deal, right? So when your blood comes through, you want to make sure that it has a bunch of air in your alveolus that you're not exhaling so that you can offload it, right? You don't want to be out of step. You want the air to be in your alveolus at the same time that the blood is moving by so it can exchange. If you happen to be exhaling when the new blood moves by, there's nothing to exchange there, right? Because your alveoli are not full of air. So you coordinate the filling of your alveoli with the movement of your blood through the capillaries. Okay, so it's a coordinated two-step. So let's take a look at how the oscillation of some of these pressures. So first of all, we're going to be taking a look at the pulmonary arteries. So these are the arteries that are basically coming to the lungs from the right ventricle, the pulmonary system, that's full of deoxygenated blood. So it has low partial pressure of oxygen, right? Because the tissues have already sucked off all that oxygen, they've used it. They've picked up a lot of CO2 from the system, so they're high in CO2. And then as they go through the system, then the concentration gradient causes the oxygen to move into the blood from the alveoli and the CO2 to leave the blood and go into the alveoli so that you can breathe it out. So you get exchange of oxygen and CO2, essentially a recharging or an oxygenation of the blood, and then a scrubbing, if you will, of the CO2. So it loses its CO2 and it picks up oxygen. So we already mentioned before that the blood coming into the pulmonary artery circuit is not purely deoxygenated blood, right? So we do have some mixture in the systemic circuit with oxygenated blood. Remember we talked about some of those arterial shunts where the arterial blood just dumps right into the venous blood. So you have oxygenated blood dumping into the venous blood. And of course, if you didn't pick up all the oxygen as you went through capillary beds, then you didn't wring all the blood dry of oxygen. You just take what you need and you let the rest of it pass. So if you don't need a lot, then the blood is literally just going through the capillaries with a lot of oxygen still in it, and it basically goes into the venous system. So as a result, what you have is this mixture of oxygenated with deoxygenated blood from these different passageways, these conducting passageways as they're sort of passing through. Because of that, it actually lowers the partial pressure of oxygen as it enters into the systemic circuit because of this mixture. So it's not quite at 100, it's actually coming in more like around 95, right? So having some of this sort of deoxygenated pollution, if you will, if you want to call it that, kind of brings that from 100 to 95 in terms of its partial pressure. That's still pretty good, because then when you get to comparing the partial pressures out into the tissues, right? This is the point of supply. So we're loading up the trucks with our product, that's oxygen. And now we're going to go deliver it to the tissue. So once we get out to the tissues, the partial pressures there are a little bit different, right? So for instance, partial pressure of oxygen in the tissues, that is the fluid, the interstitial fluid of the tissues, is coming in around 40 millimeters of mercury. The CO2 partial pressure is around 45 or so. And at this particular point, the concentration gradients are flipped. They favor now CO2 going into the blood and oxygen coming out of the blood. So they're going, and all they're doing is just going down their concentration gradient. So let's take a look at this in pictures. So from the pulmonary side, this is basically where you're picking up your supply. You have the pulmonary artery blood coming in, where you have a PO2 of 40 and a PCO2 of 45. Inside your alveolus, you have fresh air, where the partial pressure of oxygen is at about 100, right? That's what's available. And then your CO2 is around 40. And so when this comes into play, you can see 100 is much, much larger than 40. So naturally the oxygen goes down its concentration gradient and enters into the capillary, bringing that ultimately up to 100. But because of the mixture of blood, that'll come down to 95. Okay. And then the CO2, notice it's 45 coming into the pulmonary arteries. It's only 40 in the alveolar airspace. So it'll basically exit into the alveolus. So you have CO2 getting offloaded, oxygen getting loaded up. So coming out of the pulmonary system, now that you become pulmonary veins, because you're heading toward the heart now, you've become oxygen rich and now CO2 poor. So you've picked up a ton of supply. Now you're ready to jump on the distribution system and start distributing this out to the needy demand. So here now is out into the capillary beds. This is basically where you have now out to the screaming demand. So coming into, this is the arterial system, you have a PO2 of 95, right? That's because of the mixture of deoxygenated blood, whereas the tissues are only at 40. So clearly your pressure gradient favors the exit of oxygen out into the tissues, who are the ones needing the oxygen. And then your PCO2 in the tissues is 45 versus 40 in the arterial system, which favors the movement of CO2 into the capillary. And then that brings the venous side of the capillary to 40 and 45 for oxygen and CO2 respectively. And then what do? You go right back to the pulmonary side of the heart and you do another exchange. You drop off your CO2, you pick up some more oxygen, you go to the left side of the heart, you get redistributed out to the rest of the body. And this is what you do over and over and over and over and over and over. So when you're looking at gas pickup, and this is we're looking at the point of attachment. Typically, we're looking at tissues, right? So we're looking at, first of all, the transport of oxygen and CO2. Now, here's the problem. We have a lot of water in our plasma, but the problem is both of these guys are non-polar, which means that's not a good fit, right? Because most water is polar. Polar does not play well with non-polar. So these do not work well in water-based systems, okay? So, and not only that, but you don't have enough solubility in plasma to actually pick up oxygen. So you can't just dissolve oxygen in your plasma and CO2 in your plasma and just carry them that way because it's not efficient, right? There's a reason why CO2 does not want to dissolve in your Coke. That's the reason why we have to pressurize it, right? Because CO2 does not like to dissolve in a water-based system, and that's what your Coke is. So what do we have to do? We have to figure out different ways of carrying our gases, and that's basically where red blood cells come into play, because these guys are responsible for transporting oxygen and CO2. And essentially, they're going to be moving this throughout your blood. So this is what they do for a living, your red blood cells. And they do it in particular with hemoglobin. So hemoglobin is the protein whose job it is to bind to oxygen. And by the way, it also binds to carbon dioxide as well. But the important thing about hemoglobin is this, and we talked about the structure of hemoglobin, where it has 4 globin subunits, 2 alphas and 2 betas, and each of them has a heme group in it with a complexed iron, and this iron is the one that binds to the oxygen. And so this is important because when the hemoglobin is bound to oxygen, we refer to it as oxyhemoglobin. But the important thing about this is hemoglobin's binding to iron is a reversible reaction. That means it lets go. Now, this is very difficult, right? Because the ability of a protein to bind to its substrate is something we call affinity. So an enzyme's affinity for its substrate typically has to be fairly good. Usually, most enzymes have a one-way affinity. It's like a selfish little toddler, right? It's like they bind to their toy very strongly. It's like, no, you're not going to get this away from me. And that's what you want most enzymes to do. Generally speaking, most enzymes either have a very strong affinity for the substrate, they bind to it very tightly and they don't let it go, or they have a very weak affinity for their substrate, which means they don't bind it very well at all, and they're easy to separate from. It's very unusual to find a protein that can basically facultatively switch between both states. That is to say that it can easily and seamlessly switch between a high affinity state, mine, versus a very low affinity state. Oh, here, go ahead, you can have it, right? And so what we're asking from this protein is, under certain circumstances, to be as greedy as that little toddler who says, mine, right? But then when the circumstances change, be as altruistic and philanthropic as the giver. Here, take it. It's my cherished possession, but take it. That doesn't exist in a toddler, right? You have one, but not the other. But we needed both of them to actually exist in hemoglobin. So this is a very rare protein. And all that, but in each red blood cell, you have nearly 300 million hemoglobin molecules. That's why you can bind to lots of oxygen. So let's take a look at this affinity issue with hemoglobin. So a couple of things that affect hemoglobin, and what we refer to as saturation. So a saturated hemoglobin is maximally full of oxygen. So it's bound up oxygen in all 4 subunits. So it's full. That's because it has a very high affinity for that oxygen. But there are some things that affect affinity. Factors affecting hemoglobin's affinity. So how is it that you can get hemoglobin to be very strongly possessive of oxygen in some circumstances, and then to be very freely and willing to give it up in other circumstances? Well, these are the factors that do it. First of all, one thing that affects hemoglobin's affinity is the partial pressure of oxygen in blood. That's a good one. So if you have a very low partial pressure of blood, then you want that to change hemoglobin's affinity, so it naturally wants to give it away. That way you can fix that partial pressure issue. Your blood pH, right? That's associated with CO2. Again, you want that CO2 metric to change hemoglobin's affinity so that hemoglobin will naturally want to pick up that CO2 and take it off. Temperature will affect the affinity, and also the metabolic activity of some red blood cells. So let's take a look at this. Let's take a look at some of these factors up close and see how they change what's called the saturation curve. So that is to say how hemoglobin binds to oxygen, its affinity essentially. So basically a saturation curve is an enzymatic thing. It's something we do for all enzymes to measure how strongly an enzyme is possessive of its substrate, right? And so it's a graph that takes a look at the saturation of hemoglobin versus its affinity versus the partial pressure of oxygen. What we noticed was that the higher the pressure of oxygen, the greater the saturation. And generally speaking, it's not a straight line. It looks something like this. It's like an S-curved line like that, where essentially you have this sort of maximal saturation sort of peaking at the plateau. So one of the things we also noticed with enzymology, another thing we can study with these saturation curves, is how these subunits behave relative to each other. And what we noticed was evidence of cooperativity. Now that's an enzymology term. What that basically means is that when you have the tetrameric subunits of hemoglobin, when one subunit binds to oxygen, it makes the second subunit's job of binding oxygen much easier, which then makes the third much easier, which then makes the fourth much easier. So once you get past that first one, it becomes progressively easier after that. That's what's called cooperativity. And so that helps because then once you're binding to this oxygen, then binding them all up is considerably fast. So you're not basically waiting desperately to get all your oxygen bound. It moves very quickly once you get that first one bound. Okay. This also basically means that when you have very low levels of oxygen, it allows you to be able to bind with greater ease oxygen. So once you get past that first one, then it synergizes the binding so you can pull out or leach out low levels of oxygen from tissues and things like that. So your oxygen then will diffuse typically from the peripheral capillaries, which have a high partial pressure of oxygen in them, to the interstitial tissues, which have a low. So you're going down your concentration gradient. And then ultimately, how much of release? So you don't release it all. You only release what you need. So how much you actually get depends on what your partial pressure is in the tissues, right? That's your demand, by the way. That's what we're talking about there, right? So how much product you pull off the shelves depends on how strong your demand is. If your demand is only very sort of, very weak demand, then you're not going to pull that much product. You're not going to pull off all 4 oxygens off of a hemoglobin. You might pull 1 or 2, and that might satisfy you. So what that means then is that as your hemoglobin goes through the capillary network into the venous side of it, a lot of that hemoglobin is still carrying oxygen. Again, getting and sort of dispelling that misperception that venous blood is deoxygenated, right? So you could carry up to 3/4 of your oxygen in a hemoglobin, and that's referred to as your reserve. So you still have that oxygen in there, and that's your reserve. And that adds to, by the way, when you're looking at blood oxygen saturation, right? When you're doing like a pulse ox, that's looking at. So basically, when you take a look at your saturation curve, we want to take a look at a couple of metrics, temperature and pH, and see how this affects the saturation curve. That's, say, the affinity of these particular things. So the first thing we're going to do is we're going to take a look at pH. So when pH drops, that means it becomes acidic. Or when the temperature rises, that basically means above core. What that means is more oxygen is going to be released from hemoglobin. What that means is it reduces affinity because it's releasing it, it's letting it go. And this gives you a rightward shift of the curve. This is what it looks like. So here's what your saturation curve looks like. You can see under normal circumstances, it kind of has this nice little S-like structure. But then when you take a look at changes in pH, here's your normal physiological pH right there. That's normal. Notice that when your pH drops, it has a rightward shift, which is a drop in affinity. And when it shifts to light, it becomes alkaline, it increases affinity. You become more greedy for your substrate, and it shifts the curve to the left. Notice what's happening though. These pH changes are not huge changes. We're talking about less than 1 unit of pH change. Very subtle, very small pH changes will shift your affinity back and forth. It's one of the reasons why pH balance in your tissues is critical. Okay. Now, when the temperature rises, it does the same thing. See the temperature one. Here's the temperature one. So here's roughly about core right here. Right. So when the temperature rises, it goes up. So you see an increasing temperature. It also decreases your affinity. As it cools down, it increases your affinity. That means you get more greedy for your substrate. You're not going to let those oxygens go. And so you can see then you get much more greater oscillations of temperature, but heading up to 43 degrees, that's getting danger zone. Notice how you have a lot more tolerance for colder temperatures, right? I mean, you're dropping down greater amounts of temperature versus the heat. You don't get very far with the heat before you start suffering consequences. And that's because our body core temperature is already wired right up there at the edge of our maximum tolerance of heat, core body temperature heat. Then, of course, as the pH rises, it's going to have less release, which basically means a decrease, an increase in affinity. Sorry. It's greedy for it now, and it's going to shift left. Same thing if the temperature gets cold. You're going to hang on to those oxygens, and you're going to shift left. So basically, the pH effect is what's called the Bohr effect. So this is essentially that your saturation curve will shift either right or left based on the pH change. And how do you actually regulate your pH? We had a pH of 7.4. We shifted it with 7.2 and 7.6, right? So when you're regulating your pH, you're looking for a physiological pH of 7.4. But how do you regulate your pH? Well, you regulate it with your carbonate buffer system, right? So we talked about this a little bit before. If you take carbon dioxide, you mix it with water, an enzyme called carbonic anhydrase will turn this into carbonic acid. Then this will dissociate, as all acids do, into bicarbonate of sodium bicarbonate fame, baking soda fame, and of course your hydrogen ion. This causes the acidity. And so these are all reversible. So you can go back and forth. So if you get a little acidic, then you can push it in this direction and solve that problem. Or another thing you can do is you can just dump this in your urine, and that'll also remove your acidity. So it's this carbonate buffer system that actually allows the framework, the foundation for you to be able to manipulate and regulate your physiological pH. We'll see in the next chapter as well that this is also the main mechanism that you use to make your stomach acid. Okay, so a lot of manipulations there. So temperature increases, basically hemoglobin releases more oxygen. With a decrease, it holds on to the oxygen. And then this kind of allows you to be able to sort of change your affinity for your hemoglobin based on what's going on in your external environment. So the carbon dioxide transport, then, that was oxygen transport for the most part, right? So now we're going to look at carbon dioxide transport, because we did say that hemoglobin can do this one as well. And it can. But what carbon dioxide does is basically carbon dioxide is transported by binding not to the amino acid structure, the protein structure of the hemoglobin. So it doesn't bind to the same place as oxygen. It binds off-site to the protein. There's three major ways that you carry CO2 in your bloodstream. We've already established that CO2 is not a candidate for plasma delivery, right? Because it's nonpolar. So one of them is it's actually embedded into that carbonate buffer system we just talked about, right? So it's basically dumped into carbonic acid and becomes part of that buffering system. And so a certain amount of your CO2 you hang on to maintain and to regulate that pH. Another portion of it is actually bound to hemoglobin, right? To the protein portion of hemoglobin. And then a portion of it is dissolved in plasma, a very small portion. So let's take a look at these relative portions. Let's take a look at carbonic acid formation. So embedding it into your carbonate buffer system. This accounts for nearly 3/4 of your CO2. So most of it is actually converted into carbonic acid by carbonic anhydrase. And then it'll dissociate into your hydrogen ion, your bicarb ion, and you can use that to essentially manipulate your pH. Okay. Now, in addition to this, one way you can manipulate pH is hydrogen ions will bind to hemoglobin, so they're not going to be actively contributing to acidity. The bicarbonate ions can actually dissolve into the plasma, and they can be used physiologically to balance things out. So for instance, here's a good example. Whenever you're basically moving ions around, remember you're also moving around charge, right? Positive or negative charge. And so when you're losing like a negative charge around, then oftentimes what you'll do is you'll use the bicarbonate ion because it is negatively charged as a balancer. So if you move the bicarbonate around, you can balance it out with what's called a chloride shift. You basically use chloride, which is also a negative ion, to basically sort of counterbalance that ion, right? So for instance, if I take a bicarb and I want to move a bicarb over here, if I move it over there, I'm going to accumulate negative charge, right? That's not good, because if I move a lot of bicarb over there, I'm going to accumulate a lot of negative charge. Pretty soon, I'm going to get the makings of static electricity, and I'm going to shock myself at a physiological level. That's not a good idea, right? So what I have to do is I have to balance charge. If I want to move my bicarb to one position, I want to balance out that charge. So what I do is I take something that's already ready to label, which is the chloride, because we eat a lot of sodium chloride, and I just basically move the chloride over here. What does that do? That balances the negative charge. I moved a negative to one side, I moved an alternative negative to the other side. That's called chloride shift. And we see that whenever we're trying to balance charge. Okay? And we will see that a lot, actually, in the next chapter. About a quarter of it is going to be bound into hemoglobin. And so it's going to be bound to the actual protein portion of hemoglobin. When we do that, it's called carbaminohemoglobin. And so that's another quarter of it. So hemoglobin will actually hang on to it. And then the last bit of it, by far the lesser bit of it, is only 7%. So less than 10% is going to be actually directly dissolved into plasma. So if we were relying on plasma, we would only get about less than 10% of our CO2 moving around. That's not a very good efficiency level. Okay, so it's those three are our main CO2 mechanisms. Our buffer system is a huge, huge deal. Okay, that's our primary buffer system. So that's kind of what it looks like for those of you who like the visual sort of a thing. So here you basically have your CO2 diffusing into the bloodstream, and a good chunk of it, 93% of it, right, is going to be going into the red blood cell. The other 7% is going to be dissolved directly into plasma. And then of that 93%, a quarter of that is going to be attached to hemoglobin, is carbamine hemoglobin. The other is going to be converted into the carbonate buffer system, where it'll dissociate into hydrogen ion and bicarb. And then this can be used to manipulate whatever you want to do, to balance your pH, to manipulate your pH, to create an acid, like in your stomach's case, or to balance out other movements that would create a charge imbalance so that you can do this whole chloride shift sort of a thing. And so all of these things are useful. So it gives you a lot of utility with your CO2. So CO2 isn't just trash. It actually goes to work in other ways for us. So this is kind of what it looks like if you take a look at this. So what we have over here is basically oxygen pickup. This is the pulmonary side of things. So you can see a red blood cells coming through a capillary. And then the concentration gradients are going to be favoring the input of oxygen as it's being taken up by the red blood cell. It's going to be binding to hemoglobin cooperatively, right? Under the direction of all of those different metrics that changes affinity, for instance, things like pH and partial pressure and things like that. So it's going to be binding to oxygen, governed by those parameters and those criterias that change its affinity. Part of this is going to be going into plasma, but a very small percentage of it is going to be going to plasma. Then what's going to happen is going to be moving out into the capillaries through the systemic circuit. So that's essentially the business of chapter 20, right? Basically, how do you distribute this blood out to the rest of the body? Once it gets out to the rest of the body, then the concentration gradients are going to favor the movement of oxygen into the tissues who need it. Oxygen is also going to be coming out of solution and basically going into the tissues. And that's basically going to be because you have a change in partial pressure of oxygen, which is going to change the affinity of hemoglobin. You also have slight changes in pH and things of that nature, which also changes the affinity of hemoglobin as well. And then you're also going to be picking up CO2. This is your CO2 pickup. So CO2 is going to be coming from the tissues. A portion of that, 7% of that's going to be going directly into the plasma. The 93% is going to be going into the red blood cells, where roughly a quarter of it is going to be bound up by hemoglobin to become carbaminohemoglobin. And the rest of it, 70%, is going to be going into the carbonate buffer system, where you can use that to manipulate different types of pH regulation and construction. Then which is going to be going back from the capillary through the venous system, back to the heart, through the pulmonary side, right? And then it's going to be going and being delivered back to the lungs, where the partial pressures will change again, which favors the exit of CO2 from hemoglobin, who will let it go now. And it'll come out of the carbonate buffer system because of the change in partial pressures that's going on here. And it'll come out of solution from the plasma, and it'll be exhaled out into the alveolar space. And then you do it all over again. Wow, that went fast. I felt like an auctioneer on that one. But if you understand this one, you understand a lot. Okay, if you can rattle that off like this, you are in a good place. Okay. So what about some control? So let's take a look at this, right? Because we always want to talk a little bit about control, because we're basically trying to maintain a balance of blood flow in order to generate oxygen delivery, but also we want to make sure that we don't blow up capillaries and things of this nature. So we have depth of respiration, the rate of respiration. So how deeply do you breathe? How often do you breathe? And how do you get that blood flow coordinated with the oxygen delivery, right? So you want to coordinate all these sorts of things. So you have to coordinate these. And so when you take a look at local regulators, you have a couple of things that are triggers for regulation. So for instance, rising CO2 levels, this will have the effect of relaxing the smooth muscle and arterioles. Remember, these are the resistance. This will decrease your blood pressure in the capillaries, and it'll increase, because you get a higher diameter, the blood flow as it goes into the capillaries. So that basically favors better exchange, because you got more blood flowing through the capillaries to do the exchange with. You also have the lung perfusion with alveolar ventilation, right? So this is that coordination of the movement of blood through the capillaries on the pulmonary side of things with the flow of blood. So coordinating to make sure that when the blood comes through to do the exchange, there's air in the alveoli in order to exchange with. That's what this is about. then the CO2 levels will also control bronchoconstriction dilation. So if you recall, there's smooth muscles around the bronchioles themselves that basically allows you to constrict the bronchioles. And so that bronchoconstriction dilation is controlled by CO2 levels as well. And that's the culprit behind asthma when they inappropriately constrict, right? We use inhalers to relax those muscles so you dilate those passageways a little bit. So what about the nervous center, right? Obviously, we've got nervous construction, nervous output, and it's going to be affecting both cardiac output and, of course, your respiratory rates. So you got to go after both of those. And part of this is interesting, right? Because in your cardiovascular system, it's mostly involuntary, but your respiratory system has a combination of both voluntary and involuntary. So, I mean, do you have to think about breathing right now? No, you just do it, right? So that's the involuntary part. If I tell you to hold your breath, can you? So that's the voluntary part, right? So you do have some voluntary control over these involuntary components. So we're going to be taking a look at some of the involuntary components, starting off, first of all, of course, with some of the respiratory centers that you find in the brainstem, in particular in the pons and the medulla oblongata, which basically are communicating. They have motor neurons that will actually go to the respiratory muscles, including the diaphragm, which is controlled by what's called the phrenic nerve. And it'll basically cause these muscles to contract for inhalation. Now, your respiratory centers basically come in a couple of forms. Remember, there's always going to be these sections. And I'm not going to have you guys tease apart all the specific nuclei, the reticular formations, things like that, right? But you guys may recall the reticular formation from AMP1. If you guys got to that, but there are other nuclei as well in the medulla oblongata and the pons that basically represent these respiratory centers. This is the reason why, if you notice, for keeping track, there's an awful lot going on in the medulla oblongata and the brainstem in general, right? You've got your cardiovascular centers there already. You got your respiratory centers there already. This is the reason why, if you damage your brainstem, you are cooked, right? Because there's all these autonomic systems on there. So what these centers will do is they'll regulate your respiratory muscles, including your diaphragm, and they'll also be connected to sensory information. So you have sensory input because you don't just want to breathe, you want to breathe in response to what's happening in your environment, which means that you have to know what's going on in your body, right? And so that's always in touch. And we already talked about a couple of these guys, right? We talked about that central chemoreceptor who's bringing in intelligence from the body about oxygen levels, CO2 levels, and pH levels. And so it's kind of got tabs on all of that. We'll talk about that one again here in just a second. But these respiratory centers that you see, you actually can divide, and typically the big ones that we're going to look at are in the medulla oblongata. You can divide these into two different groups. The first one is called the DRG, or the dorsal respiratory group. And so this is an important one. And we have the ventral respiratory group. And this is just because of their position in the brainstem. But these two, basically, between these two, they'll actually set your pace of respiration. So when you're talking about your respiration rate. So let's take a look at what these guys do. So the DRG is what's referred to as your inspiratory center. This is the one that basically causes you to inhale. It functions in quiet, and I can't stress that enough, and forced breathing. So this is the one that's in control of tidal breathing. So who's telling your phrenic nerve to tell your diaphragm to contract so you can take in a breath? It's the DRG. At rest, during quiet breathing, your DRG is the one that's firing. So like right now, when I take a breath, it's firing, and then it stops firing, and then I relax and I exhale. And then it fires, tells my diaphragm to contract, and I inhale, and then it stops, and then I exhale. It also is true for force breathing. So if I do a force inhale, my DRG is also involved in that one as well. So the ventral respiratory group is basically your inspiratory and your expiratory. So it's both. But it's only forced breathing. This is not tidal. Why? Because, okay, let's take a look at this. Why is the DRG just inspiratory? Why not expiratory? Because inspiration is the only active version, right? Expiration is passive, right? The way to inhale, inspiration is to contract. That's DRG. But expiration is just relaxation. It's just your passive relaxation of your diaphragm. So all you need is one signal. Inhale, stop. Inhale, stop. Inhale, stop, right? But when you're forcing it, you have to go both ways. So you have to inhale forcefully, and you have to actually forcefully exhale, which means you're contracting all those muscles, those respiratory muscles, including your diaphragm and your skeletal muscles, to basically force the air out. So what you're doing is you're forcing your lungs open and you're squeezing down on them forcefully. That's the reason why VRG is involved in forced breathing. It's like you're squeezing, literally squeezing yourself to get that forced air out. Okay. So basically the DRG is going to stimulate the inspiratory muscles. And then ultimately, once they stop, then you get exhalation. So the moment of exhalation is when the DRG stops and then the diaphragm relaxes. That's quiet breathing, basically, in a nutshell. So this is kind of what it looks like for quiet breathing. So your DRG is activated. The diaphragm and your intercostal muscles will contract because they've been stimulated by the phrenic nerve. And then what happens is the DRG is inhibited, so it stops. And then what happens is you get the passive exhalation or the passive relaxation. Passive exhalation associated with passive relaxation of the diaphragm, the external intercostal muscles. And then you just basically fire off your DRG again for your next breath. Okay. So if you're not breathing tidally, you're not taking in that inspiratory reserve, that means there's damage to your DRG. Yeah, that's not a good situation. Now in forced, basically what happens is you have increased DRG, which also then stimulates the VRG to kick in. So it's got basically calls for backup. And so it also recruits not just the diaphragm, but accessory inspiratory muscles, right? We talked about those, didn't we? We talked about the scalenes, the sternocleidomastoids, pretty much everybody who's involved in opening up your rib cage to sort of allow for the expansion of your lungs. So all these guys get recruited in there as well. And then this gives you active, and then after inhalation, your expiratory center neurons will actually stimulate active exhalation. So not only that, but you also contract these muscles so that you can, other muscles, so that you can squeeze down on your rib cage to sort of squirt out or force out the air. So this is what it looks like. So for forced breathing, you've got the DRG and the inspiratory version, the side of the VRG are activated. And then ultimately your expiratory is inhibited. So this basically is going to force contraction of the inhalation muscle. So you get a forced inhale. And then what happens is the inspiratory version of VRG and the DRG are inhibited. You turn on your expiratory center of VRG, which is going to be a forced, contracted exhale. And the inhalation muscles are relaxing at this particular point. And so you get your forced exhale. So VRG is largely for forcing your breath. DRG is for tidal. So there's a couple of other centers, however, that are also important, right? Because ultimately these two, DRG and VRG, just basically establish normal tidal breathing and also forced breathing. But what about rates, right? Well, who's responsible for accelerating your respiratory rate or decelerating your respiration rate? Well, that basically gets us to the pons, right? So before we were in the medulla oblongata, now we're in the pons, and you have two different centers in the pons, the apneustic center and the pneumotaxic center. So the apneustic center, what this basically does is it provides continuous stimulation of the DRG center. So this is the stimulator of DRG. The pneumotaxic is designed to inhibit the apneustic center. So it's a braking system for the apneustic center. And so it'll be a promoter of exhalation. So it reduces inhalation and it promotes exhalation. So this is another layer on top of already the DRG and the VRG. So that's great. So we got a middle manager. What do we achieve with that? Well, what we achieved now is the ability to communicate and to connect these systems to our sensory inputs, okay? So when you take a look at your normal DRG, VRG interplay, this gives you your basic pace and depth of respiration. So that's happening with just VRG and DRG. The pneumotaxic center is the one that will modify the pace. So this is the pace modifier. So establishes rate. So the question comes, okay, great. So the DRG stimulates the contraction of the diaphragm and things like that. So who tells the DRG to fire? Well, it's the apneustic center that tells the DRG to fire. Okay. And then the pneumotaxic center is your braking system. It's the one that basically antagonizes the apneustic. So this is kind of what it looks like. So here you can see your nuclei in the pons. So here is your pneumotaxic center, your apneustic center. You can see the pneumotaxic will inhibit the apneustic. But there are other centers in the cerebral cortex, the limbic system, and the hypothalamus, which will also have some play on this, right? So basically what happens is you have different inputs from your brain that will either stimulate the pneumotaxic center, shutting down your breathing, or it'll inhibit the pneumotaxic center, increasing your breathing rate, depending on the inputs. Right? This is one of the reasons why when we get emotional, we start breathing heavy. Is because of that input, that control from the limbic system. And then of course that affects the apneustic center, which then affects the DRG and the BRG. The other one to remember is our big central nervous system, our CSF chemoreceptors are also in here communicating to these guys as well. Remember, they're communicating issues of pH, oxygen, and CO2 saturation. So this is the intelligence division. This is what we see out here in the body that you need to be aware of. And so when you take a look then at this bottom nuclei, this actually is the DRG and the BRG. So here you can see the lower one is going to be the DRG, the upper one is the BRG. You can see all these inputs coming in here and kind of connecting to them. So you can see the DRG and the BRG is basically sort of the grand central station of all of this. And they're getting inputs not just from the apneustic center and the pneumotaxic center, but also from the chemoreceptor, the central chemoreceptor, but they're also getting inputs from other nerves. For instance, vagus nerve is collecting information, both sensory and sending out motor, and bringing it into this particular region, this particular DRG, BRG region, right? So you basically have communication through the rest of these receptors, for instance, the stretch receptors in the lungs, which are communicating back to this to say, listen, you need to stop inhaling because you're going to pop your lungs like a balloon, right? So that's communicating back to the DRG to say, stop, or you're going to blow your lungs up. Let yourself relax and exhale, right? So that's necessary communication because these guys don't know when you're overinflating your lungs. And that's important information. You also have your glossopharyngeal, right? So this is another branch of vagus coming in, and glossopharyngeal. And they'll basically, this is bringing in other information from other peripheral chemoreceptors. So wait a minute. Now let's take a look at this. It's already got the CSF chemoreceptor up here. That's the main chemoreceptor. Now it's got intelligence coming in from the peripheral chemoreceptors that are spread around throughout the rest of the body. So this DRG cluster, BRG-DRG cluster, is receiving a truckload of information from everybody. It's basically got its fingers on the pulse of everything that's happening. Whether it's in the body, it knows what those oxygen and CO2 levels are, what the pH levels are. It knows what's going on in the CSF thanks to these central chemoreceptors. It knows what the apneustic and the pneumotaxic centers are hearing from the cerebral cortex, the limbic system, and hypothalamus. And it's basically taking all this information in, and that's informing the activities of this DRG-BRG group. So when you're breathing, it's taking this all into effect. And then, of course, it's sending out those communications to the rest of the body. So you can see that going through the motor neurons to the diaphragm here. So this is your phrenic nerve that connects directly to the diaphragm. And then you have other motor nerves that connects to your intercostals. So to these guys right here. Now, the important thing to understand is because of this hookup, because of all this intelligence, and because of the voluntary versus involuntary nature of it, you have some control over it, but not total control over it. If I told you to hold your breath, could you? If I told you to hold your breath indefinitely, could you? Like, even if you wanted to, could you? Right, which is actually kind of an important physiological thing. Well, death is always interesting, right? Because it's basically an ultimate physiological fail. And cause of death is always interesting. But when you're drowning, right, one of the things that people don't realize is that when you're under the water and you realize you're in trouble, you're holding your breath, right? But you know, first of all, you're not going to be able to hold your breath forever. Why? Because what happens is, as you hold your breath, your oxygen levels are going down, your CO2 levels are going up, your pH levels are going down, your chemoreceptors spread throughout your body are on high alert because they're saying, whoa, wait a minute, oxygen's cratering, CO2 is going up, this is not good. It's sending those communications to the DRG and the VRG. You're getting the same thing from the central chemoreceptor as well. And at some point, that becomes so screamingly dire that the DRG and the VRG basically make a reflexive gulp. So the first gulp of air, or the first gulp you take when you're drowning, it's not like people are down there like, you know what, screw it, I've had a good run, let's take it all in, right? It's not like that. What happens is you take in that first gulp of air reflexively because your chemoreceptors get to such a high tilt that it forces your respiratory nuclei to take over. It's like, listen, I know you're voluntarily holding your breath, but you will die if you continue to hold your breath. So we're going to take a breath. I'm going to override you, and I'm going to involuntarily make you take a reflexive gulp of air. That's what happens, is you take that reflexive gulp of air, and once you hit that, then the water in your throat causes your cough reflex to kick in, and you start coughing out and expelling all the air that's in there, and you take in more water, and then it's just a spiral down. And generally speaking, once you get oxygen saturation levels that start cratering, especially to your brain, likely you'll start convulsing, and you'll just kind of like that for a while, and then eventually you're gone. But that happens very quickly. And actually, there's one movie that had that right physiologically, that had that process right. And I forget what it was. It was some movie, I want to say Dennis Quaid or something like that. They were like in a submarine trapped or something like that, and you had to like swim through a corridor that was underwater to get to another hatch to save somebody. And it was like a one-way trip. He was going to be able to get her out, but he wasn't going to be able to get out himself. And the way he acted that out was literally exactly what it would look like. I mean, he even had it to where he had the reflexive gulp. You could see like that. You could see the reflexive gulp, and then he started like doing the coughing thing, and then he did the convulsing thing, which you do when your brain starts losing oxygen. And then he did the dead float, and that was an amazing thing to see him like. That's spot on. Somebody's seen somebody drown, unfortunately. That's what it would look like. But if you're wondering, it would go quickly. You're not around for very long. It'll be uncomfortable at first because you're taking in that gulp of water, but it will be gone. You will be gone quickly. You know, we know, how long does it take for you to black out when you have head rush? Like if you have a really, really bad head rush, like you get up really fast, how long, and it's like you're kind of like blacking out, how long does it take? Seconds? I mean, literally, like when you stand up, you're like, okay, wait a minute, I'm getting a little woozy, I'm getting a little weak, and all of a sudden it kind of starts getting, black, and you grab onto something, right, so you don't fall. And then if it gets really bad, you can actually feel your body kind of twitching. That's the convulsing part of it, right? Until finally your blood kind of catches up. That's just your blood trying to catch up to your brain. So when you're drowning, likely your blackout would happen very quickly, literally within seconds. So I don't know if that's a comfort or not, or if that's just more frightening, but that's kind of physiologically what would happen. So basically your respiratory reflexes are all wrapped around your chemoreceptors, sensing your partial pressure of oxygen, CO2, and of course your pH, and of course your baroreceptors, going after your blood pressure. So all this information is coming in to these. And by the way, don't forget stretch receptors. And we got 3 different stretch receptors going on: chemo, baro, and stretch receptors. All of these communicating to the system so that you can basically sort of adjust your respiratory rate. Other things that can cause a reflex are irritations, like chemical irritations, things of that nature in your nasal cavity. So your sneeze reflex, your cough reflex will do that. Other things as well, like pain and things of that nature, those are less frequent. So unless you've had, core body injury or something like that. So these are things that will actually kick in and be reflexes that will sense what's happening to yourself. So the chemoreceptors, typically speaking, are in major conversations with your respiratory nuclei. So they're listening very carefully to the respiratory nuclei. So these are the ones that really cause the problem. And like we said before on the previous graph, they're being communicated by the glossopharyngeal and the vagus nerve. And then the central chemoreceptor is monitoring your cerebrospinal fluid. We talked about that one last time as well. And then the glossopharyngeal is coming from your carotid bodies, where we talked about that a little bit. So you're looking at blood pH and also the partial pressure of oxygen in your carotids as it's coming to these. And the vagus nerve is going to be hanging out in the aortic bodies. So these are bringing stuff from your heart, your blood pH from your heart, and of course your partial pressure of oxygen also from your heart as well. Now, what happens if you have too much CO2 in your system? This is what's called hypercapnia. And so ultimately, this will stimulate your chemoreceptors, and then it'll basically offload that CO2 to restore homeostasis. And we'll take a look at that here in just a second in one of our homeostatic cycles here in just a second. If you have too little CO2, it's called hypocapnia. So you have hypoventilation. And so this is basically where you have an abnormally low respiratory rate. So it allows CO2 to build up because you're not getting it out. So if you're not breathing at a normal respiratory rate, you're not going to be able to push out that CO2. It's going to build up in there, and it's going to create kind of a hypercapnic situation where you have an increase in CO2. If you hyperventilate, that means you're breathing too fast. It's an abnormally high respiratory rate. Then you're going to get hypocapnic. Why? Because you're basically pushing out a lot of CO2. You're kind of getting all that CO2 out, but it gets a little on the lowish side, so that becomes hypocapnic usually. And so your chemoreceptor is going to pick this up, and then it's going to trigger that, send that message to your respiratory centers to slow it down. It's like, okay, whoa, slow down, because you're getting a little crazy here, right? So you don't want to be hypo or hyper. You want to be in your homeostatic norm for CO2. So this is kind of what it looks like. So you have your normal CO2. If you increase your CO2 levels, like so for instance with hypoventilation, you're not breathing enough, then you're going to have an increase in CO2. This is going to do a couple of things. First of all, it's going to stimulate those chemoreceptors in your arteries. It's also going to decrease your pH in your CSF, which is going to stimulate your CSF chemoreceptors, the central chemoreceptors. The arterial chemoreceptors are going to ultimately stimulate the respiratory muscles, which will increase your respiratory rate, and that will breathe out your CO2, and you'll get yourself back down to homeostatic norm. So this is basically what you're looking at. This is going to be when you have a peak response. The trough response is when you have a decrease in CO2. So you're going to have an increase in pH. So it's going to be a little acidic on that side. You have inhibition of your arterial chemoreceptors. So the pH change in the CSF is going to cause a reduction in stimulation of the central chemoreceptor, and an inhibition of the respiratory muscles, which is going to slow down your breathing. And that's going to allow you to bring your arterial pressure back down to normal. So this is a trough response. Okay, so that's how you keep your CO2 into homeostatic norm. The baroreflex is what you talked about already. We already know that these guys are in carotid and aortic system. So basically what's going to happen is as the blood pressure falls, your respiration increases. So you increase your respiratory system. As it increases, your respiratory decreases. So notice it's inversely proportional. To each other. So as blood pressure goes up, respiratory rate goes down. So you slow it all down. And that leads us to the last slide that we have, which is the Herring-Brewer reflex. This is a simple one. This is like basically baroreceptors that are involved in kind of an inflation-deflation boundary. So this sets the boundary for inflation and deflation. So as your lungs fill up with air, it's going to hit stretch receptors, and that's going to kick in the inflation reflex. And this inflation reflex will stop inhalation. So you do not exceed the capacity of the lungs to overinflate, right? So you don't overinflate them. The deflation reflex is just the opposite. It stops exhalation. So you don't over deflate or collapse the lungs. So basically, it stops deflation. So it sets the upper bound of the lungs and the lower bound. So that's the Herring-Brewer reflex. So it's a reflex that actually stops it. So you don't do that. Okay. That is respiratory. Now, digestive. So digestive system, no rest for the weary, right? So the digestive system basically is structured after, it's basically a big long tube, that's your gastrointestinal tract, right? With an in hole and an out hole. And then of course there's accessory organs as well. So we're gonna start off first of all, by basically journeying through the gastrointestinal system by first starting with eating. So we're gonna eat something. Now, the important thing to understand is the digestive system has two different things. Digestion and absorption. However, there's two different types of digestion. There's mechanical, which is physical force, grinding up the food like mortar and pestle. And then there's chemical. So the first task is swallowing. You got to chew your food, right? So first of all, you're going to take the hamburger. And you don't eat the entire thing at once, right? You take off a small bite of it. And then you start chewing it. In chewing in your mouth, you've got both mechanical and chemical. Why? Mechanical because you are mechanically grinding it up into a smaller and smaller food bolus, right? And chemical because you're mixing it with your saliva, which has enzymes in it. And not only that, but you're trying to liquefy it into a paste. Then once you get it to a manageable place, then you get ready to swallow it. Swallow it is referred to as deglutition. Lay that one on your friends at a party. That'll totally get you uninvited. Right? But this is deglutition. And so there is a voluntary component of it. So you can choose whether or not to swallow. But then at some point, there's also an automatic involuntary component to it. It's divided into three basic phases. There's the buccal phase, named after the buccinator, right? That's basically in your facial muscle. There's a pharyngeal phase and an esophageal phase. So let's go ahead and take a look at each one of these. So first of all, we're going to take a look at the buccal phase. So in the buccal phase, what's going to be happening is you're chewing it up in your mouth, mixing it with your saliva. It's become a nice, pasty, soft mass. Now what you do is basically you take with your tongue and you move it back to the back of your throat beyond your soft palate, which we refer to as our gag zone, right? Our gag reflex back in that area. And so at this particular point, what happens is as we move this to the back side of our throat, the food crosses the line from voluntary to involuntary. You don't have to think the food down, do you? All you have to do is move it to the back of your throat, and then it automatically goes down, okay? And so the buccal phase is associated with you chewing it. So this is what's happening in your oropharynx. You're chewing it, mixing it up with your saliva, mixing it up with your enzymes, and then once it's nice and ready to swallow, you move it to the back of your throat, and it hits that reflex. Once it gets taken over by the involuntary, then it hits what's called the pharyngeal phase. The pharyngeal phase is going through the oropharynx, or excuse me, the palatopharyngeal zone. And then what's going to happen is it's going down the esophagus now. So there's no getting it back here. So notice one thing that it does is that little guy right there is the epiglottis. So let's take a look at him. Normally the epiglottis, which is elastic cartilage, is open. So this basically allows for air to come through the nasal cavity and into the trachea. But as the food goes down, the food actually hits that little epiglottis flap, and that epiglottis will bend down and close off the trachea, opening up the only thoroughfare for the food, which is through the esophagus. This is basically how you manage to not choke to death when you swallow. Because the epiglottis will close off the trachea, the food bolus will go down the esophagus on the way to its stomach. So this is the pharyngeal phase. It's in the back of your throat now. Then it'll move into the esophageal phase where it gets down beyond the trachea. It's moving down into the chest. And so it's moving by peristalsis, which is muscular contraction. This is waves of coordinated muscular contraction as it moves down toward the stomach. And then finally, you get the transition to the stomach, where the food bolus will literally be squeezed like a tube of toothpaste, like you're squeezing a tube of toothpaste. Basically, you're squeezing this little food bolus down into, and it'll drop into the stomach, into the cardiac region. And then right here is a sphincter, the lower esophageal sphincter, which closes off the stomach from the esophagus. This is also referred to as the cardiac sphincter. And a lot of times you can feel this process rather unpleasantly. If you've ever swallowed a horse pill vitamin or something like that, like sideways. How many of you guys have done that one? Right? It's gone down the wrong way, and it's like, you're like, you can breathe just fine. It's just like, it feels like there's a rock in your throat, and you're kind of waiting and waiting and waiting, and eventually the feeling disappears. You can feel it going further down, and then eventually it disappears. That's when it enters the stomach. Yeah, that feeling just, it's really creepy. But that's it. So now that we're in the stomach, this is going to be a big one. So we've gone from the mouth to the esophagus, right? So we've squeezed that food down in there. And now we're going to be entering the stomach. And so the stomach, functions of the stomach, have a couple of things. First of all, we always know the stomach as a storage receptacle for food that we've eaten, right? Because that makes a lot of sense. However, the stomach is going to be doing a lot of mechanical digestion, right? So remember, in the mouth, you did mechanical and chemical. In the stomach, you're doing a lot of mechanical. In the esophagus, you didn't do anything really. You're just moving it from point A to point B. So you didn't really do a lot of significant digestion there. And you'll do a little bit of chemical, because you do have some enzymes in the stomach that we'll talk about that you actually produce in the stomach. And then you also have what's called intrinsic factor that's actually produced. This is a big one. This is big enough to where it has its own bullet point. So the production of intrinsic factor is a glycoprotein. And what it does is it helps for the absorption of vitamin B12. Why is that important? Because vitamin B12 is what creates heme. Of red blood cell fame, the heme group, it's a vitamin B12 derivative, which is one of the reasons why when you get a vitamin B12 shot, you get a little boost of energy. Not because you have any energy, but because that you get a little bit more heme, which means you're binding more oxygen, which means you're delivering more oxygen, which means you're getting more energy from the oxygen you deliver. So it has nothing really to do with energy directly. It just basically sort of fills out your capacity to bind oxygen. So those are some of the major functions of the stomach. And so when we take a look at the anatomy of the stomach, you can take a look at it. It's basically a J-shaped organ with a lesser curve, which is the concave curve, and a greater curve, which is the outer curve on the lateral surface. And so ultimately, this has different regions to it. We'll talk a little bit about the regions, right? So the upper region where the lower esophageal sphincter exits the food bolus is called the cardia, or the cardiac region. Then the bulbous region is the fundus. So if you take a look at your esophagus, it kind of comes into the stomach, looks something like that. So this is the cardia. This region up here, that bulbous region, is the fundus. The body is represented by the bulk center of the stomach, and then the pylorus is the tail piece that connects to the small intestines, right? So those are the major regions of the stomach itself. So here you can see, here is your cardiac region. You can see there's the input of the esophagus right there. Your fundus is up there. It's kind of pointing away from us a little bit. The body is sitting right there in the middle of us, and the pylorus is down here. And of course, down here, you've got your pyloric sphincter. And up here, you've got your lower esophageal sphincter. So your lesser curve is going to be this inner curve there. And then the greater curve is the outer portion of the stomach. That's the greater curvature. So when you take a look at the musculature of the stomach, which is important, remember all of these systems where we talked about the 4 layers of the digestive system in lab, right? We said that you start off with the mucosa, right? The mucosal layer, and then you have the submucosum, and then you have the muscularis externa, and then you have the serosa. And so all these layers are composed of those 4 layers. And everybody has, remember, those circular and those longitudinal muscles in your GI tract. The difference is the stomach, which actually has not 2 layers, but 3 layers. So it's got basically also oblique as well. So it's got longitudinal, circular, just like everybody else in the tube, but it's also got oblique muscles as well. So it's got an extra 3rd layer of musculature in the muscularis externa. And what this does for us in this muscular layer is it provides for 2 of the major types of muscle movement in the GI tract. There's 2 of them. The first one is peristalsis, right? We said that this is the wave-like movement that is directional. So what does that mean? That means if I'm like the esophagus, which is a perfect peristaltic area, and I've got a food bolus in here, in order to move this food bolus forward, what I have to do is I have to sort of close off the back end, right? And then I have to squeeze right there, just like a tube of toothpaste, right? You just squeeze like a tube of toothpaste. So generally speaking, what happens is this area has already been contracted, but before I let that relax, what I'm going to do is I'm going to squeeze it again. And so it can't go this direction because it's already contracted. But when I squeeze it again, then it's going to move that direction. And then if I squeeze it again, it's going to move that direction. I squeeze it and squeeze it and squeeze it and squeeze it So basically what I'm doing is I'm contracting in a wave, right? So here's my wave. I contract, it squirts this way, but I keep this one contracted while I contract this one. That forces it to go forward, not backwards. So I contract it again, and then I let this one go. And then I contract this one and it squirts forward. And then I contract this one and it squirts forward. So basically what I'm doing is this kind of wave-like contraction as I squirt it and push it in that direction. That's peristalsis. That's how the chyme and the food moves through your digestive system from point A to point B. The other big one is what's called segmentation. This is kind of like the sloshing movement. And this is what the stomach does a lot of. So imagine I've got a food bolus here, but now what I want to do is I want to kind of mix it up a little bit. So what I want to do is I want to slosh it back and forth. So now what I do is instead of doing that sort of wave-like contraction, what I do is I put the food bolus in between, and then I kind of do like a washing machine. I squeeze this one, it shoots in this direction. And then I squeeze this one and it shoots it back. I squeeze this one and it shoots in this direction. I squeeze this one and I alternate. I go back and forth. And basically what's happening with the food bolus is it's going sloshing back and forth, back and forth, back and forth, because I'm like shooting it back and forth in between these. What that's doing is it's mixing it up. I'm mixing that up really good, and it's basically getting that pasty food bolus into more of a liquid type of a form. So that's segmentation. It's more of like a mixing wave. And that's what the stomach does a lot of. So that's all basically around the muscularis externa. So it has the muscularis mucosae, which is associated with the muscularis layer. But then the externa is going to be the one with the 3 layers. So it has your extra oblique layer of smooth muscle. One thing I want to point out about the anatomy of the stomach, though, before we move on, is the inside liner, the epithelium of the stomach, is actually arranged at these like little ridge-like grooves. Those are called rugae. And why do you have those ridge-like grooves? To increase surface area, so that you'd have more working space inside your stomach itself. So you guys will see this when you open up the cat's stomach. So a lot of times you can see those rugae grooves in there. So let's take a look at the histology, shall we? Because we're never that far away from histology, are we? Okay. So basically, when you take a look at the epithelial liner, the mucosal liner of the stomach, it is going to be simple columnar in nature. Okay, so that means it's basically looks like this. And you guys saw this histologically in lab. This lines the stomach. And so this is a sheet of cells. Some of them will produce mucus, and that's really, really important because this becomes like the liner of the stomach. To protect the mucosal epithelium. Right, because remember, acid will burn tissue, so you have to protect your stomach liner from the acid that is produced. And so you secrete this thick mucus as a protective barrier from that acid. The other thing is it creates gastric pits, which are basically these invaginations of the epithelial surface. And it's surrounded and it's aligned with cells. There will be mucus cells. There will be different cells down there that will be actively making acid or enzymes and things like that. So you have cells typically at the base of the neck that's basically bubbling up mucus into the actual liner area of the stomach lining itself, so in the actual stomach itself. So we take a look at some of the gastric glands. These typically are going to be associated with the gastric pits. And there's 2 different cell types in the gastric pits that we see in these gastric glands. The parietal cells, which basically make acid, and the chief cells, which make pepsinogen. We'll take a look here at pepsinogen here in just a second. But those are the 2 dominant cells. There are other cells in there we'll talk about a little bit. But those are the 2 dominant ones. So here you can see you've got your 4 layers. So here's your mucosa. Your mucosal epithelium is basically arranged in these gastric pits. So you can see this is your lamina propria here in the middle. with your vasculature. So you can see there's capillaries there feeding all of these cells. And you can see these deep invaginations. They're almost like mine shafts, like those really, really tiny little mine holes, those ventilation holes in mine shafts that go down. So it's kind of like those. They're basically deep little wells of invagination that go down into these gastric pits, these areas down here. So you can see you got collar cells and you got deep, deep pit cells as well. And so the lamina propria is basically forming the connective tissue between these gastric pits and kind of maintaining the integrity of the wall of it. And then, of course, you have your muscularis mucosae here, which marks the boundary of the mucosal layer from the submucosal layer. Typically, stomach will have a fairly normal submucosa. So you have a lot of connective tissue here with vasculature. So you have capillaries and lymphatic vessels both in this region. And then the muscularis externa has your two different muscle types. So here's your circular muscle and your longitudinal muscle, but then you also have this layer of broken oblique muscles as well. That gives you an extra layer of musculature for the segmentation contraction that it does. And then, of course, you have this tough connective tissue layer, the serosa, on the outside. And so that's kind of what it looks like. But let's take a look at the business end of it. So we zoom in on the gastric pit. So this is a gastric pit. This is what it looks like. So up here, you can see these are the mucus producing cells. Here's the lamina propria right in here. The mucus producing cells will create mucus. These will look like goblet cells if you take a look at them closely. And they're producing mucus that basically bubbles up and kind of covers the liner of the stomach, protecting it from the acid. In addition to that, you're also going to see these sort of orange triangular cells here. These are the parietal cells. And then the chief cells are the blocks of pink cells. That's these guys. And then right at the base of the pits are another type of cell called G cells. We'll take a look at those guys here in just a second. And then every now and then you do see some smooth muscle interspersed in there for like just local undulations of the gastric pits, like if they need to move around or something like that. So basically what's going to happen is in the parietal cells, you're going to be busy making two things. Intrinsic factor, number one, where we talked about intrinsic factor, this is a B12 coabsorbent. And then it's going to also make the hydrochloric acid. This is the stomach acid. So these guys are critical, right? These guys are making your stomach acid, and they're also making intrinsic factor, which you need in order to get your B12. If you don't have intrinsic factor, you don't get B12. You don't have B12, you don't have heme. You don't have heme, you don't bind oxygen, you're dead. So intrinsic factor is critical, critical, critical. The chief cells, on the other hand, which there's a lot of them, are basically secreting pepsinogen, which is an inactive enzyme, which is a protein cutter. So this is a proteolytic enzyme that digests proteins. So the proteins that you eat, it digests them. So the ogen basically means it's in an inactive form. So it has to be activated. And that's what the chief cells are making. So let's take a look with the last few minutes or so of class to take a look at exactly how the parietal cells make stomach acid. This is kind of cool, actually. So here is your parietal cell in your gastric pit. What it does is it basically starts with what we already know, the carbonate buffer system. Your CO2 plus your water with your carbonic, not carbonate, but carbonic anhydrase, we learned about this in the last chapter, right, is going to combine together to make carbonic acid, which will dissociate into your hydrogen ion and your bicarb ion. Now, what do you do here? Now what you do is you take your hydrogen ion and you actively transport it into the lumen of the gastric gland. This is inside the lumen of the pit. So your hydrogen ion goes in there. What is that? That's acidity, right? So you're pumping actively the acidity into your gastric pit. Here's the problem, however. When you do that, you lose a positive charge, right? So you have to deal with that. So your bicarb, on the other hand, is going to be actively transported into the bloodstream, right? And that's going to basically make it a little more alkaline. But here you're moving negative charge. So that's a problem, isn't it? On one hand, you're moving positive charge. On the other hand, you're moving negative charge. You got to balance those out. So in comes chlorine. Chlorine is like, oh, wait a minute, you moved a negative charge out. So instead of becoming overly negative, then we're going to shift that chloride into the parietal cell. That balances out the negative charge distribution. It distributes and then basically leaks out. This is basically a leak channel, just leaks out naturally and goes right into the lumen of the gastric gland. And that basically will cancel out the positive charge of the hydrogen ion, which means you're neutral again. So the reason why you have hydrochloric acid in your stomach is because, not because you have a bunch of hydrochloric acid in there, like you drank a bunch of hydrochloric acid. That's not what it is. The reason why you have hydrochloric acid in there is because the chloride is there to, number one, balance the movement of bicarb into the blood and to neutralize the accumulation of positive charge due to the hydrogen. You've accumulated hydrochloric acid in your gastric gland. That is exactly the way that you manipulate your pH, is by moving stuff around and balancing your charges and things like that. So pepsinogen, which is being produced by the chief cells, basically has to be converted into its active form, which is pepsin. And so once it actually gets activated into its active form, pepsin, then it can go and it can digest proteins, which means that you're also dumping pepsin into the gastric gland. So your gastric juice is essentially this witch's brew of hydrochloric acid from your parietal cells and pepsin from your chief cells. And that's the bubbling brew that's basically accumulating in your gastric pits. And then from there, basically what you have is this bubbling acidic brew, basically kind of bubbling up. Have you ever seen like one of those boiling mud pools in a volcanic area where you kind of see the mud just kind of bubbling up? That's kind of probably what the opening to a gastric pit looks like, where you have kind of like this sort of gastric juice, this acidic enzyme-laden gastric juice coming out of the gastric pit. The problem is, if you're there looking at it, you're probably what got eaten, which means it's coming for you. Okay. So let's take a look at some of the pyloric glands. So this is in the pyloric region. This is the inferior region of the stomach. So you're going to be producing a lot of mucus here all throughout the stomach. By the way, you're going to be producing a lot of mucus. But in addition to this, you also have in your gastric area, you also have a couple of other cells, G cells, whose job it is to produce gastrin, which regulates hormonally the gastric phases. And there's a few of them. And you have also what's called D cells, which basically release what's called somatostatin. And so this is an inhibitor of gastrin. So you have gastrin, which regulates the gastric phases of your stomach, the activities of your stomach, when it's going through the churning, when it stops, when it's ready to move it forward. So all those activities of what the stomach is doing is regulated by gastrin. And the somatostatin is basically going to be feeding back, and it's going to be inhibiting gastrin, which basically shuts down your gastric phase, which is something you want to do before you start moving what you just had in your stomach on through your small intestines. So you have to shut down your gastric phase in order for your intestines to take over. And then that's really what kind of starts to kick in. So in terms of the phases that we just talked about that are being controlled by gastrin, we have a couple of different levels of control. I just want to intro this one. And what we're going to do is we're going to start off by breaking all these guys down next time as we sort of walk our way through them, because this is a really, really important section of the actual chapter itself. But control of this activity is controlled by your central nervous system. It's actually controlled by the vagus nerve. But what happens is the vagus nerve basically turns over autonomous control to what's called the enteric nervous system. You may have remembered this from AMP1, but the enteric nervous system is basically kind of like a wholly owned subsidiary of the autonomic parasympathetic system. So there's so much going on. There's so much control and regulation that needs to happen that the parasympathetic system basically says, listen, enteric nervous system, why don't you guys just run with the digestive stuff? I'm going to turn all that over. I'm going to give you the autonomy to do what you need to do and the authority to make the decisions you need to make. So you just run everything digestive. It's all on you. I am delegating it all to you. I'm going to worry about the respiratory system and the cardiovascular system and the urinary system. You completely take over the digestive system. And that's what we refer to as the enteric nervous system. It's kind of like an entirely delegated branch of the parasympathetic system. And it's driven by not just neural reflexes, but also hormonal regulation as well. And this is part of what both neural and hormonal governs and regulates the phases of gastric control, along with gastrin. Gastrin is an example of a hormonal controller, but there's also neural. And the first phase is what's called the cephalic phase, which then leads to the gastric phase, which then leads to the intestinal phase. And this is the progression of what the stomach does in progression. And so what we're going to do is we're going to basically take a look pictorially and break down what's going on both neurally in terms of neural control and hormonal control as we go through each of these three gastric phases. That make sense? And we're about our witching hour. Could go all day, but I know you guys can't. So